Aluminum nitride isn't just a material, it's the silent hero of the 21st century. While silicon gets the credit for running our devices, aluminum nitride is the high performance backbone that keeps that silicon from melting. From the 5G tower sending data to your phone to power systems in electric vehicles, this specialized ceramic is the reason our modern technology doesn't overheat. In nature, heat and electricity usually travel together. Metals like copper are great at moving both, but in electronics, that's a problem. You want to pull heat away without causing a short circuit. Aluminum nitride is a rare contradiction. It can move heat as fast as metal while acting as a total electrical insulator. It's a high performance, safe alternative to toxic materials like beryllium oxide. Heat doesn't move through the ceramic using electricity. It moves through tiny vibrations called phonons. For, for the best cooling, these vibrations need clear, straight paths. However, oxygen is the ultimate enemy. Even tiny amounts of oxygen act like microscopic roadblocks, scattering the heat waves and slowing everything down. In the world of aluminum nitride, staying pure is the one way to stay powerful. Creating high purity aluminum nitride takes extreme engineering. This material is made in massive furnaces reaching 1,750 degrees Celsius. That is 300 degrees hotter than flowing volcanic lava and much hotter than the melting point of steel. In this white hot heat, nitrogen gas is pumped into build a rock solid structure that is incredibly stable. There are two distinct paths to create aluminum nitride powder, and the choice changes everything. Direct nitridation involves taking solid aluminum metal and reacting it directly with nitrogen gas at high heat. It's a faster, more affordable process, but the resulting particles are often jagged and can contain higher levels of oxygen. On the other hand, the carbothermal reduction method is a premium choice for electronics. It starts with aluminum oxide mixed with carbon. This method is much slower and requires more energy, but it produces incredibly consistent spherical particles. Because these spheres are uniform, they can be packed together more tightly later in the process, resulting in a much higher quality finished product. The carbothermal process uses chemistry as a cleaning tool. By mixing the raw materials with carbon at intense heat, the carbon acts like a magnet for oxygen. It literally pulls the oxygen atoms away from the aluminum and carries them off as gas. This leaves behind a perfectly clean aluminum base, ready to bond with nitrogen in its purest form. The journey starts as a fine flour-like powder. To turn this dust into a solid part, engineers mix it with binders, basically a high-tech glue. This creates what's known as a green body. At this stage, the part feels like a hard eraser, solid enough to be moved around and shaped, but it hasn't reached its full strength yet. When the goal is to create a complex three-dimensional part, engineers use injection molding. The aluminum nitride powder is mixed with a heavy amount of wax or plastic to create a feedstock that flows like liquid. This mixture is injected under high pressure into precision carved mold. Once it cools and hardens, you have a perfectly shaped part. From tiny nozzles to rounded heat sinks, this that would be impossible to create by simply pressing the powder. For the flat plates used in computer chips, we use tape casting. The aluminum nitride powder is mixed into a liquid slurry that looks like a thick paint. The liquid is poured onto a moving belt and passes under a very precise blade that spreads it into a perfectly thin layer. As the liquid evaporates, it leaves behind a flexible, leather-like sheet of aluminum nitride. This tape can then be cut into squares or circles with incredible accuracy. Before the ceramic can become hard, the glue must be removed in a process called binder burnout. This is a slow, agonizingly careful bake. The temperature is raised just a few degrees at a time over many hours or even days. If the heat rises too fast, the liquid binders will turn to gas too quickly and build up pressure. This can cause aluminum nitride to develop microscopic cracks or even explode. The goal is to let the gas breathe out of the pores slowly, leaving behind a fragile brown part made of pure powder. Once the glues are gone, the furnace hits its peak temperature for sintering. During this stage, the individual grains of aluminum nitride begin to soften and grow into one another. It's like thousands of tiny ice cubes melting just enough at the edges to fuse into a single solid block. This part actually shrinks by nearly 20% as the air gaps disappear. This transforms the object into a fragile cluster of powder into a single rock-like solid piece of high-strength ceramic. The finished product is incredibly tough. On a scale of mineral hardness, aluminum nitride ranks at 9, which is just below a diamond. While it's much harder than steel, it's a ceramic. It can handle incredible heat but is brittle. A hard, sharp hit could shatter it like glass. Because aluminum nitride is so hard, normal metal tools are useless. A steel drill bit would be ruined in seconds. Shaping these parts requires tool tipped with industrial diamonds. These machines grind the material with a microscopic precision, making sure that the surfaces are flat enough to fit perfectly onto computer chips. One of the most amazing things about aluminum nitride is how fast it reacts to heat. An aluminum nitride heater can jump in temperature by 115 degrees Celsius every single second. This instant speed is vital for DNA testing and high-speed manufacturing, where every split second of heating or cooling matters. As our gadgets get smaller and our power needs grow, the demand for aluminum nitride is exploding. It is the thermal backbone for aerospace radar, high-tech armor, and the future of clean energy. It is the silent hero keeping the modern world from a total meltdown. These are the sources I used: aluminum nitride preparation methods review and aluminum nitride ceramic materials, all you need to know. And then the images were created using Google Notebook LM.